In this video, we're going to be discussing calculus and parametric equations. This corresponds to section 7.2 out of the OpenStax Calculus book, volume 2. There are 4 learning objectives for this section, but we're only going to cover 2 in this video. The first thing that we're going to discuss will be to determine derivatives and learn how to find the equation of a tangent line for a parametric curve. This is the first learning objective in this section. We're skipping the second, which is to find the area under a parametric curve. The formula is in the textbook if you want to learn about it, but we simply don't have time this semester to study every single topic. The second learning objective that we will talk about is how to find an equation for arc length on a parametric curve. The last one, which is applying the formula for surface area to a volume generated by a parametric curve, we are also going to skip. This leaves us basically with 2 separate ones that we're going to evaluate. If we're looking at it, that means that we're going to be looking at derivatives and equation of tangent lines for parametric curves and how to find the arc length of a parametric curve. The first thing you need to remember about parametric curves, and in fact that you need to remember even if you're working in polar coordinate systems or even spherical coordinate systems, is that the derivative is always, without exception, dy dx. In other words, the derivative is defined on a rectangular coordinate system to be the change in y with respect to the change in x, and it doesn't matter what coordinate system you're using. If you're in a parametric equation, which is written in terms of t, this could cause a little bit of a problem. This requires us to use complex fractions and the chain rule later on. When we're looking at the derivative for a parametric equation, since the derivative is always dy dx, we can use complex fractions to rewrite dy dx as dy dt divided by dx dt, since of course, if we were to abuse the notation, which remember is a very common thing to do, if we did 1 over dt over 1 over dt, this would be equal to the value of 1. Thus, we're rewriting dy dx in the form of dy dt over dx dt. Does it really make sense to write this as if it were a fraction? No, of course it doesn't. This is a derivative operation. But the genius of Leibniz's notation is that it does work if you think of it as a fraction, though in fact it is an operation. Because we can write it in this complex fraction form, we can then pull it apart and take the numerator fraction, which of course is not a fraction, and divide by the denominator fraction, which of course is not a fraction. This means we need to take the reciprocal of the denominator fraction and multiply by it. If you look at it in this form, and we again abuse the notation, you'll see here that the dt's cancel, which gives me back what I started with, the derivative of y with respect to x. This is, of course, an abuse of notation. These don't actually represent fractions, but the genius again of Leibniz's notation is that we can treat it this way and solve it this way. That means that if you want to find the derivative, you will take the derivative of the y equation with respect to t and divide it by the derivative of the x equation with respect to t. Now this does only work provided that both derivatives exist and the denominator derivative is not 0. If that is true, then we'll be able to find the derivative in parametric form. In a physics class, you would interpret this formula that you see here slightly differently. You would say that the slope of the tangent line to a curve at a given point is equal to the vertical velocity, dy dt, divided by the horizontal velocity, dx dt. So even though it is an abuse of notation, it does have a real-world meaning. We want to remember what exactly the tangent line equation is. Recall this is just the point-slope form of a line, the variable y minus the y coordinate of a known point equal to the slope at that point times, in parentheses, the variable x minus the x-coordinate at the point. The point is x1, y1. M represents the slope of the tangent line. The slope, of course, is the first derivative at that point, x1, y1. In example 1, we want to find the equation of the tangent line to the following parametric curve at the given point. The parametric equation is x equals 2 times the cosine of t and y equals 5 times the sine of t. These are both equations in terms of the independent parameter t. There is a restriction on the value of t that it must be between 0 and 2 pi, including both endpoints. The point at which we want to find the equation of the tangent line is 0, 5. I've gone ahead and produced a graph of the parametric equation using Desmos for you here. If you locate the point 0, 5, you'll see that it is right here at the very top of what is, in fact, an ellipse. Since the derivative here at the top looks like it should be, in fact, 0, since it does appear that the tangent line there at the top would be a horizontal line, then I'm anticipating that the derivative there is 0. Let's use our formula and see if that is, in fact, what we get. Scrolling down, you will see that I have produced a graph. In this second graph, you'll notice that I have actually labeled the point. Whenever you do this, you will enter the point as an ordered pair inside parentheses. Make sure you click on the box label, and it will put the label and the point you're interested in on the graph. For a point like 0, 5, that's not really very important. But if the point were something like the square root of 2 times or 5 divided by the square root of 3, I would really need a label to know where it is. Now let's use our formula to compute the derivative. In parametric form, I have 2 cosine of t, y equal 5 sine of t. Recall our formula for the derivative. Our formula for the derivative is the ratio of the derivative of y with respect to t divided by the derivative of the x equation with respect to t. Let's compute that now. In order to do that, I need to look at first the y equation and find its derivative with respect to time. That means that dy dx must be equal to, well, the derivative of sine is cosine, so it must be 5 cosine of t for the derivative of the y equation with respect to t. The derivative of the x equation with respect to t would be -2 sine of t. This will give me the equation for the derivative of this particular parametric equation. Now, this does not give me the derivative at the point 0, 5. To compute the derivative at the point 0, 5, I would also need to figure out what value of t puts me at 0, 5. I can do that a couple of different ways. One way to do that is to simply set it equal. In this case, I know that x is going to be equal to 2 times the cosine of t. Since I want the x value to come out to be 0, then this means that it must be equal to 2 cosine of t, or cosine of t equals 0. Now there are 2 places in the interval between 0 and 2 pi where the cosine of t is 0, at pi over 2 and 3 pi over 2. In order to know which t value it is, go ahead and plug it into the y equation. The y equation is 5 sine of t. I know, however, from my point that the y value is 5. That means 5 must be equal to 5 sine of t, which means the sine of t must be equal to 1. The only angle that gives me both of those values is, of course, if t is equal to pi divided by 2. If t is equal to pi divided by 2, then I will know what the value is. In that case, I can plug that into my derivative. That would be my next step. let's plug in the value of pi divided by 2 and replace the t with that value. This gives me the derivative of y with respect to x evaluated when t equals pi over 2 is equal to 5 times the cosine of pi over 2 divided by negative 2 times the sine of pi over 2. However, I know that the cosine of pi over 2 is 0. The sine of pi over 2 is 1. This gives me 5 times 0 over negative 2 times 1, which is 0. Again, this met my expectation that in fact the tangent line there at the top of the ellipse would be horizontal, which means it has a derivative of 0. Let's take a look at a different example for the same curve, which is the ellipse, but at a different point on the curve. In example 2, we want to evaluate this at the point square root of 2, negative 5 square root of 2 over 2. You'll see that I have added this in to my Desmos file as a simple point, which you see here. Notice it has approximated the radical in a different form. I want to use the formula for the derivative again, so I can simply borrow what I've done above, which is this value right here. I can copy and paste it and continue. In this equation, we're going to look at a slightly different way of evaluating what the derivative is. Instead of finding the angle t, this time I'm going to do a substitution. Since I know the derivative formula is 5 cosine of t, but I know that x is equal to 2 cosine of t, then I can solve for the cosine of t. If I solve for cosine of t using this equation, I should come up with cosine of t equal to x divided by 2. Similarly, I can take this equation and solve for sine of t, which would also give me the following. Sine of t should be equal to y divided by 5. If I take those two and I replace or substitute cosine of t and sine of t with these equations, I get the following formula. This gives me 5 times x divided by 2 over sine of t would be negative 2 times y divided by 5. This is a formula which I could simplify if I wanted to using the rules for complex fractions. This would instead give me 5x over 2 times the reciprocal of the denominator, which would be 5 over negative 2y. In this sense, I could rewrite it as 25x divided by negative 4y. This is an expression for the derivative in terms of x and y only. Now I can take the points, which are in terms of x and y only, and replace them in this formula to see what value for the derivative I come up with. By doing that, I would get the following. dy dx evaluated at our point P should give me 25 times the square root of 2, which is the x value, divided by negative 4 times negative 5 square roots of 2 over 2, which is the y value. Rewriting it into complex form, I have 25 square roots of 2 divided by 20 square roots of 2 over 2, which reduces to 10 square roots of 2. If I write it in this form, notice that the negative 4 and negative 5 gave me 20, which divided by 2 is 10, which gives me a common factor of square root of 2. The square root of 2's will cancel, and I can also reduce the common factor of 5 from 25 and 10 to come up with the final answer for the derivative at that point, which is 5/2. Now let's go ahead and put this into the slope-intercept form of the line. The equation for my line in this particular case is going to be x minus the y value, and the y value is negative 5 square roots of 2 over 2. Oops, I put the 5 in the wrong place. Negative 5 square roots of 2 over 2 equal to the slope 5/2 times x minus the x value, which was the square root of 2. If we rewrite this in a different form, what would this look like? If we move the -5 square root of 2 over 2 to the other side, remembering, of course, that a double negative here is going to make a plus, then we can get the following. You'll see that I have moved the constant term from the left side of the equation to the right. Combining these two terms now, which are both constants and already have a common denominator, would give me the equation for the tangent line at that point in slope-intercept form. Since they're identical and I'm doubling, that would eliminate the divided by 2 and simply give me -5 square root of 2. This means that it should be crossing the y-axis at roughly -5 square root of 2 with a slope of +5/2. Let's go back to the graph where the point was and see if we agree. If I were to take this graph and put a line on it that corresponded to the tangent line, can you believe that that line would have a slope corresponding to 5/2 and would cross the axis at 5 square roots of 2 negative? I think it does, and in this way we've been able to find the equation of the tangent line at a particular point. In example 3, we want to find the derivative formula for the following parametric curve. This one is not at a particular point, just in general, what is the derivative? You'll notice surprisingly that when I put it into Desmos, this parametric equation given by x equal 2 sine squared of t and y equal 3 cosine squared of t actually gives us part of a straight line. In fact, it's giving us the straight line extending between two ordered pairs. The two ordered pairs are at 2, 0 and 0, 3. You will notice that, in fact, if you put this into Desmos yourself, it traces this multiple times while t goes from 0 to 2 pi. We don't need to find the derivative at a particular point. We just want to find it in general. However, we should anticipate that since this parametric curve actually is producing part of a straight line, the derivative formula should in fact give us the slope of that line. We can use these 2 points to compute the slope, or you can simply count it out. It has a fall of 3 and a shift to the right of 2. The slope here on this line is -3 divided by 2. Let's see if we get the same formula using the derivative formula for parametric equations and our equation. The equation is here, and let's copy down the formula for the derivative with parametrics as well. I've copied and pasted both our original formula and the derivative formula in parametric form. Remember to find the derivative of the y equation with respect to t and divide it by the derivative of the x equation with respect to t. In terms of what I have, this would give rise to the following formula. dy dx, which is the derivative, would be equal to the derivative of 3 cosine squared of t with respect to t. This involves the chain rule, which would bring the 2 to the front times 3 cosine of t multiplied by the derivative of cosine, which is negative sine. Then we would need to divide this by the derivative of the x equation with respect to t. This also involves the chain rule. The 2 power would move to the front to multiply by 2 sine of t, and then I would need to multiply by the derivative of the inside function. Derivative of sine would give me cosine of t. Once I have these, the rest is simply a matter of algebraic simplification. This gives me a -6 sine t cosine t in the numerator. In the denominator, I would have 4 times sine t cosine t. That makes sine t and cosine t common factors between the numerator and denominator. They will cancel, and this will leave me with the fraction -6 divided by 4, which reduces to -3/2. That is exactly what we expected it to be up above. Let's take a look at the next section. In this part of this video, we want to think about what it means to have a horizontal tangent line. A horizontal tangent line, of course, occurs when the derivative is 0. In this case, because we're dealing with parametric equations, we have the ratio of two derivatives with respect to t, dy dt divided by dx dt. That means that we can get a horizontal tangent line on a parametric curve provided that the derivative of the numerator, dy dt, is 0, and the derivative of the denominator, dx dt, is not 0. The only way to get 0 out of a fraction is, of course, to have 0 in the numerator and not 0 in the denominator. What about a vertical tangent line? Let's think about what it would mean to have a vertical tangent line on a parametric equation. A vertical tangent line occurs wherever the first derivative is undefined. A vertical line has undefined slope. Since we're dealing with parametric equations and we have the ratio of two derivatives with respect to t, this means that we will get a vertical tangent line whenever the denominator derivative dx dt is equal to 0 and the numerator derivative dy dt is not 0. In other words, when we have not 0 divided by 0, we know that this is undefined, and that's what gives us our vertical tangent line. What about finding arc length? We did arc length much earlier this semester when we were looking at various curves and trying to find out how long it was along a particular curve from one x value to another or from one y value to another. That's basically what arc length means. If you could straighten out the curve and put a ruler along it, how long is that section? These were the formulas that we found earlier this semester for computing arc length. In both formulas, we needed to find the first derivative. When we're doing it with respect to x, it's the normal dy dx or f prime of x. When you're doing it with respect to y, however, it is f prime of y, not f prime of x, which is basically the reciprocal derivative dx dy. Now we can do some manipulation and write dx and dy in this format. This is an abuse of notation since the derivative is an operation and not a fraction. However, this is again the genius of Leibniz's notation. It works, so we do it. This means that I am basically, in my head, canceling the dt's to get dx equals dx. This doesn't really have any meaning since, of course, this is a derivative operation. However, we can use this to replace the dx differential in the first representation of arc length and the dy differential in the second representation of arc length. Now let's see what we should do after that. If we then rewrite the 1 in a different form so that it is the denominator squared divided by itself, in the first arc length formula, dx dt quantity squared divided by dx dt quantity squared, and in the second, dy dt quantity squared divided by dy dt quantity squared, this will give us a common denominator between the two parts underneath the square root. Because they're common, we could factor them out of the square root. When you factor out a perfect square, remember that you must come up with an absolute value. This will give you 1 over the absolute value of dx dt from the first form of arc length with respect to x, and 1 divided by the absolute value of dy dt from the second form of arc length, originally with respect to y. Once we have this, however, As long as we're tracing in the positive direction and we don't trace our curve more than one time, we'll be able to drop the absolute values. In the worst case, we would simply get a negative length, which tells us that it was being traced backwards. Now, what is the positive direction? If you assume that the curve is traced from the left to the right, from smaller numbers to larger numbers with respect to x, and from the bottom to the top, or from lower y values to larger y values for the equation on the right, then you can drop the absolute values that you see in this equation here. When the absolute values disappear, then I can cancel the dx dt from the differential with the 1 over dx dt at the front. I can do the same with the dy dt in the differential on the right and the 1 over dy dt at the front. With that gone, you'll notice now that our equations are in fact identical. The difference now, of course, is where are the values going between. We have lost the sense of the meaning of the A, the B, the C, and the D. However, we've proved that it doesn't matter whether you started with the formula with respect to X or the formula with respect to Y. They both lead to the same arc length formula in parametric form. If we're looking at it in parametric form, then this does form the formula. Now let's understand what the A and the B must represent. The A and the B must, in fact, now that our differential is dt, refer to the first t value and the second t value. In other words, if we're tracing in the positive direction, t1 must be less than or equal to t, which is less than or equal to t2. This will guarantee that we can cancel out the absolute value with the fraction form of it coming from the differential. Let's apply this formula for the arc length of a parametric curve to the following parametric curve. X as a function of t is equal to the exponential e to the t power times cosine of t. The y equation with respect to t is also the exponential e to the t times the sine of t. T is going between 0 and pi. I've produced for you here the Desmos version of this particular one. Notice that the slider bar is all the way towards pi and the dot on the curve is all the way here on the left. That means that when we're looking at our curve, that is the stopping point. You could plug in the t values to determine where it begins, but I will tell you that the start is here at the coordinates 1, 0. Again, when t is 0, e to the t is 1, and the cosine of 0 is 1. Sine of 0 is 0, and that's what gives us this as the starting point. That means that it starts here and traces it in this direction, the counterclockwise direction. Remember that when you produce a parametric curve, you need to give the orientation, which is the direction in which the curve is traced from the lowest t value to the highest t value. You can also indicate them with the words start and stop, or begin and end. Let's now use the formula for arc length on this parametric curve to find out how long that arc length is. I've recopied the parametric equation down here, and I've written the equation for the arc length now in terms of T1 and T2, the low and the high value for the parameter, assuming that it's being traced no more than once and always in increasing direction. Now when we're looking at this, how can I apply the formula? To compute the formula, I will need to find the pieces dx dt and dy dt. First, I'll go to the side and compute those separately. Since dx dt will require taking the derivative of the x equation, and the x equation is the product of two functions of t, I'm going to need the product rule. This will give me the derivative of the first function, e to the t, which is e to the t, times the second, which is cosine of t, plus the second derivative, and the derivative of cosine would be negative sine of t, times again the first function, which is e to the t. I could also write this if I wanted to in a factored form of e to the t times the quantity cosine of t minus sine of t. To find dy dt, I repeat the process, but this time taking the derivative of the y equation, which also has two functions of t multiplied together and will also require the product rule. That will give me that dy dt is equal to f prime g, which would be e to the t times sine of t, plus g prime f, which would be the derivative of sine, which is cosine, times the first function, e to the t. Factoring out the common factor e to the t again, I am left with sine t plus cosine t in parentheses. Now to apply the formula, I need to square each one of these. If I square each one and I have a product of factors, it's like squaring each factor individually. I'm going to write each one of them and put them under the radical. Let's do that now. I need to then compute the following. The length of this will be equal to the integral, and in this case, we're going from 0 to pi along that entire curve, from our first t value to our upper t value. Then I need the square root of dt quantity squared. The square root, dt of course, is e to the t times the quantity cosine minus sine. That will give me e to the t squared times cosine of t minus sine of t quantity squared. The next part of the formula is to add to that the square of dy dt. Adding on to that, I would get also another square of e to the t for the dy dt, and a square of the factor sine plus cosine. At the very end, I'll have the differential dt. Notice that if I have e to the t quantity squared, I can write that as e to the 2t. Let's do that now. Be sure that you do not mistake this for e to the t to the second power. This would instead give us e to the 2t, since one base with two powers has the powers multiplied, and that gives us 2t. That means that e to the 2t is a common factor between the two terms under the radical and can be factored off and split apart as a separate factor underneath the square root. Let's write that part now. Since we can think of the square root as the 1/2 power, the square root of e to the 2t should just give us back, of course, the e to the t power. Underneath the radical that's left behind, however, in order to simplify it, we're going to have to multiply out these binomial type products. Take a moment to do that, then restart the video. By expanding the two factors underneath the radical that are being squared, I can square out the first one, which is here in green, and the second here in orange. Notice that this will give me 2 cosine squareds of t, 2 sine squareds of t, and the 2 sine t cosine t terms will cancel. That leads to the following, that I have 2 cosine squared t plus 2 sine squared t. This, of course, makes the 2 a common factor. Factoring out the 2 then will lead to 2 times the sum cosine squared of t plus sine squared of t. However, you should recognize cosine squared plus sine squared as simply being the number 1. Moving on then, this gives us the integral from 0 to pi of the square root of 2 times e to the t dt. This is a very simple integral to evaluate, since the integral of e to the u is simply e to the u. Then we need to plug in the lower and upper limit of the integration. This gives us square root of 2 e to the pi minus e to the 0 in parentheses. Since e to the 0 is 1, I end up with the final result that arc length is the same as the square root of 2 times the quantity e to the pi minus 1. If you take your calculator and approximate it, you'll find that length is roughly the irrational number, the irrational number corresponding to 31.31166 going off from there. It is not a repeating pattern because it is irrational. There are several reasons for it to be irrational. E is an irrational number, pi is an irrational number, and the square root of 2 is also irrational. Now let's take a look at the final part of this video. We want to know about finding the second derivative of a parametric curve. To find the second derivative of a parametric curve involves several steps. Because the derivative of a parametric curve is actually the ratio of two derivatives with respect to t, the second derivative is going to involve the chain rule. Here is the simplest way to rewrite the second derivative, though I realize this does not look simple. I've written it out for you so that you can follow along, and hopefully by the end of this video it will make more sense to you. In this particular problem, to find the second derivative means to take the derivative with respect to x again of dy dx. Note that the derivative is always given in terms of dy dx. Even though we're in parametric equations, the derivative by definition is dy dx. Since I can rewrite d by dx using an abuse of notation as the derivative with respect to t divided by dx dt, since, yes, I know they're not fractions, but if we thought of them that way, the dt's would cancel, I can use this in place of the second derivative with respect to x. So that the second derivative of y with respect to x, which is the derivative with respect to x of dy dx, can be rewritten with this complex notation applied to the dy dx. Since I can then abuse the notation further and simply move the dy dx into the numerator, this leaves dx dt by itself in the denominator and asks us to take the derivative with respect to time of dy dx. However, I can also remember that dy dx is in fact dy dt divided by dx dt. In practical terms, to find the second derivative, we find the derivative with respect to t of the first derivative. That corresponds to the numerator part of this particular expression. And then we divide by the derivative of x with respect to t. That corresponds to the denominator part. Let's apply this to a formula. In example 5, we want to find the formula for the second derivative of the parametric equation x as a function of t equal to t to the fifth minus 4t cubed, and y as a function of t equal to t squared. Let's apply the formula now. Let's rewrite the formula in simpler terms. Taking out the center part of the formula, we are left with the following. The second derivative of the function with respect to x both times is the derivative with respect to t of the first derivative dy dx, all divided by dx dt. In order to compute dy dx, remember that dy dx is the ratio of dy dt divided by dx dt. My first step is to find both dy dt and dx dt. To do that, I'll come to the side and write each of those out. The derivative of x with respect to t is given by an application of simply the power rule applied to the formula for x. That would give me 5t to the fourth power minus 12t squared. To find the derivative of the y equation with respect to t is another application of the power rule. So dy dt is equal to 2t. Now I take each of these pieces and plug them into the formula for the second derivative. I'll be using the last form here. Since dy dx is equal to dy dt divided by dx dt, let's write that part first. The second derivative of y with respect to x both times is the derivative with respect to t of the ratio between dy dt, which is 2t, over dx dt, which is 5t to the fourth minus 12t squared. This whole thing is also divided by dx dt again, which is 5t to the fourth minus 12t squared. In order to find the derivative of the numerator, we'll have to apply the quotient rule. I will want to go to the side to find the derivative of the numerator separately, but before I do that, I can simplify this quite a bit in the derivative process by realizing that there is a common t factor in the denominator and numerator. By factoring the t out of the denominator, I can rewrite the denominator here as t times 5t cubed minus 12t. That allows me to then cancel the monomial t factors. This will let me rewrite the second derivative as the derivative with respect to time of 2 divided by 5t cubed minus 12t, all divided by the quantity in the denominator, 5t to the fourth minus 12t squared. Now when I'm moving on to do the next part, instead of having to apply the quotient rule, I can instead do a power rule by lifting the denominator's expression to the numerator by raising it to the -1 power. Let's do that set separately. Notice that when you rewrite it in this form, only the factor from the denominator, 5t cubed minus 12t, is raised to the -1 power. The 2 came from the numerator and keeps its +1 power. Now we can apply the power rule for derivatives to this expression. This will lead us to the derivative of that numerator part being -2 times the quantity 5t cubed minus 12t raised now to the -2 power times the derivative of the inside function, which is the 5t cubed minus 12t, and the derivative of that would be 15t squared minus 12. Rewriting it again will lead to the following expression. -2 times the quantity 15t squared minus 12, all in the numerator, divided by the quantity 5t cubed minus 12t, all raised to the second power. Now let's take this final representation for the derivative of the original numerator and put it back into our representation for the second derivative. Remember that this formula came from the original second derivative formula, which is here. This was our representation for that second derivative. Now we have replaced the numerator derivative with what is here in blue. It's still being divided by the original denominator, which corresponds to dx dt in the formula. From here out, it's simply an exercise in algebra to get this into a more simplified and better form. Remember to keep track of which is the primary division bar. This is the primary division bar here in black. That means that I can separate it as the fraction in blue times 1 over the part in black. Let's rewrite that now. I've pulled apart the complex fraction into the numerator times 1 over the denominator from the primary part of the fraction. To simplify further, I need to factor out a common t squared from the denominator in the right factor. That leaves behind, well, hang on. Instead of pulling out the full t squared, let's just pull out a single t. Why would I possibly want to do that? If you look to the left, you'll see that the factor in the denominator on the left is 5t cubed minus 12t. If I take out only one t, I can write this in the same format. That will give me t times 5t cubed minus 12t raised to the first power. This gives me 3 of that binomial factor in the denominator. This will now let me write negative 2 parentheses 15t squared minus 12 all divided by t times the quantity 5t cubed minus 12t quantity to the third power. There are a couple of other things we could do to simplify it. I could pull the common t out of here. Since I'm pulling it out of something that's being raised to the third power, it would again be raised to the third power. That would give me, in this format, the t times the following: 5t squared minus 12, all being raised to the third, which would give me t to the third times 5t squared minus 12 raised to the third. In the numerator, the 15 and the 12 have a common factor of 3. I could pull the 3 out of there as well. That would give me left behind a 5t squared minus 4 in the numerator. It's tempting to want these to cancel, but they're not the same and they don't. Be sure that you don't mistake something that does cancel for something that doesn't, and vice versa. Now let's rewrite it in our final form. We'll put it in green just to contrast it from everything else we see. I got left with a negative 6 in the numerator, 5t squared minus 4, divided by a t times t cubed would give me t to the fourth. And then I would have the binomial factor 5t squared minus 12 all raised to the third power. This is probably as simple as it's going to get, and I would leave it just like that. This is, of course, a formula for the second derivative of this function. Keep in mind that this is actually on an xy coordinate plane and not on a t plane. If you want to get rid of the t, you will have to go back to the original equation here and find a way to substitute out the t. It won't be easy on this problem because we don't have t to the first. If we look at our final representation, however, in every place that t occurs, I have t squared or an even power of t. Let's take the formula for y and rewrite it so that we can get rid of the t's in the formula for the second derivative. I've copied again the original expression of the parametric equation here, and I've reproduced the formula we found for the simplified second derivative of the parametric. Again, this is with respect to y and x, though we have t left in our formula. To get rid of t, we're going to replace it with y wherever we have t squared. That means that I can come to the formula and find all locations of t squared and replace them with y. To rewrite the t to the fourth, I can think of t to the fourth as t squared squared. That will allow me to replace the t squared also with y. Let's rewrite the second derivative now without the parameter t. This would give me the second derivative of y with respect to x squared, which is equal to negative 6 times the quantity 5y minus 4 divided by y squared times the quantity 5y minus 12 all cubed. This is a pretty complicated second derivative formula. Chances are, if we were to try to solve this equation and eliminate the parameter at the beginning, the rectangular coordinate equation would be quite complicated. Whatever it turns out to be, the derivative of it is this expression right here. This is the last thing we wanted to learn out of this section, and this ends this video.